Welcome to the last lecture on transistors. So we studied already in the transistors that how the transistors works, and then what are the different modes. For example, common emitter, common base, common collector, and what are the formulas that are involved. Now we are going to do the transistor biasing. So transistor biasing is basically nothing new, but only that you have applied the batteries. So you can clearly see that you have actually applied the voltages and the batteries, which we talked about in the last class, that you have to forward bias it, you have to reverse bias it, but basically more or less you are applying the batteries. So batteries are already applied in the last two lectures also. When I told you about the transistors, batteries were still there, but we were not focused on those batteries. We were not trying to find or calculate the currents, or we were not trying to find any voltages in those that lecture, but our main concern was to look at that how the transistors is working. Now in this that I'm going to cover that how to actually calculate the currents and all of those things in your transistors. Okay, so in the last lecture I basically covered about the Kirchhoff voltage law, which is one of the very important law if you really want to solve the problems of transistors. Okay, so now I'm going to go through and explain you what are the different kind of biasing questions you will see. So there are basically four type of questions you will see in your previous year questions. Either you go for gate, you go for net, or you go for any exam. Now with transistors, there is one additional topic which is known as amplifiers. Okay, so between transistors and between op-amp, there is one small topic which is known as amplifier, but this topic is one of the very difficult topics. So for this topic, I will only give you the notes, very small notes, in which I will give you 3-4 formulas. That's it. We will not cover amplifiers too much in detail because that takes so much time and the output is very less. Because once you complete all the amplifiers, the questions are very rare which are coming from amplifiers. But basically, the after this transistor lecture, you can directly go on and do the op-amp. So op-amp lectures are already uploaded in the course, so you can actually see that how what is op-amp. Okay, so now let's dig into this lecture. So there are four methods or four type of questions which will be there, and number one is known as base resistor method. So the for the circuit for base resistor method will be something like this, and for all of the questions it will be similar kind of circuit, and you will basically see there is a transistor in middle and there is a common voltage which is being applied. So this common voltage is known as plus VCC. Now I want to make one point very clear. If you're watching this lecture, very beautiful, you are a good student, but you have to make sure one thing that after this lecture you have to read the book BK Mehta, because until unless you read the book you do not get the feeling. For some topics, I'm not saying that you need to read the book for each and every topic, but for some topics I'm very particular that you need a book reading. And at this is the point where you need a book reading, because there are two reasons. Number one, that will give you a good summary, and now after you have watched the lecture you will be very much able to understand the book very easily. And the second thing is, in VK Mehta you don't have to read everything, you have to read only what is covered in the class. And when you will see that there are many solved examples in VK Mehta, and that will actually help you in understanding the concept even better. So do those problems once you are done with that this lecture. Read the VK Mehta. It will not take too much time. It will hardly take you 1 hour if you sit down and read it. And okay. So there are four methods. Number one, base resistor method. In that method, what is happening? There is a common voltage that is being applied, which is known as plus VCC. And there are two resistors. One is base resistor, one is collector resistor, and there is no resistor in emitter. Sometimes there is no resistor, and sometimes there could be a resistor. So it is not a compulsion that there will be no resistor. There can be a resistor. Okay. So what is happening here is that this is a common voltage. So now what is happening? Let's see how the circuit is there. So number one thing we see is that the current is flowing through, and in this branch, which current will be coming? Collector current. So whatever current enters here is known as the collector current. And then here in this direction, base current is going on. So this is your base current. So from VCC, two currents are going. One is collector current and one is base current. Collector current is going to the collector of the transistor. Base current is going to the base of the transistor. And then there is this current, which is emitter current. And this thing is known as ground. You can see the lower line, that is grounding. It means it has a zero potential. Grounding means you have connected two straight to the ground. So you have taken one wire and you are directly connected that wire to the ground. So when you do that, so basically what you are exactly doing is that you are making the things, your voltage zero. So voltage at this point is 0. So N point is means 0 voltage. Okay. Okay, fine. So now let's start doing the uh, calculation. So whenever you have to do calculation, it's a same step in every transistor problem. You have to apply Kirchhoff voltage law. So now we have two loops. So one loop starts from here. So you go from VCC. So first thing you use UC plus VCC. So whenever you see plus, you have to put minus. So UC plus VCC. So I'm writing here VCC. Okay. Now it's a very good question that why I'm not putting here as minus VCC. Okay, right. I should put here minus VCC, but I have put on plus VCC. Why is that? Because now I am applying Kirchhoff voltage law in open loop. So let me explain you that so that you are well aware about the situation. So what is happening here? So I'm starting from here. So I'm writing its potential. So I'm starting from here. So its potential is plus VCC. Okay, then I'm going here. Then I'm coming like this. So I'm going in the direction of current. So I'm putting minus IB. So whenever you go in the direction opposite to the current, you have to write minus IBR. And then you come like here, come till here. And then you go in this direction. Nothing else has came. And then you go from here to here. So this is positive and this is negative. And the voltage between them is VBE. Means voltage between base and emitter. So now you are finally here. So this thing is positive. So you see the positive first, you have to apply negative. So if you see the positive side first, so you have to write the negative. So going from here to here, the voltage is VBE. But you are going from positive to negative, so that is why you have to write minus VBE. And then finally you are here. So the potential here is 0. So this is how you write it. So this is Kirchhoff voltage law in open loop. This is not Kirchhoff voltage law in closed loop. Okay. So Kirchhoff voltage law in open loop, how do you write that? So you write the first voltage. First voltage is VCC. And then you follow all the steps I taught you in the last class of Kirchhoff voltage law. So if you're going in the same direction as current, so you can clearly see I'm going in the same direction as current. So I have to put negative sign. So minus IB into RB. Why? Because voltage across this will be V equals to IR. So the voltage across this is V equals to IR, and what is I through this? IB, and what is R? RB. So IB into RB will be voltage across this resistor. And since I'm going in the direction of current, so I have to put negative minus RB into IB. And then I come till here, and then I see there is a positive and negative. So going from here to here will be minus VBE. Because I see the positive side first, so I have to put negative sign here. And then finally equals to 0 equals to the final voltage. Initial voltage, then using all the rules as such, and then final voltage. Final voltage is 0, so I put the 0. So that is how I applied my Kirchhoff voltage law in open. Okay. Now what I can do is I can bring all both of this on the other side. Okay. So then you get VCC as this. Okay. Then in the circuits we apply. So let me explain one more Kirchhoff voltage law. So we can even apply the Kirchhoff voltage law in this loop as well. Okay. So we have to apply the Kirchhoff voltage law in this loop as well. So it's also open loop. So I start from VCC. So plus VCC. And then what I do, I come down. So now voltage across this is ICRC. So I'm going in the direction of current. So minus IC into RC. Then I have to go from here to here. This, sorry, I'm sorry. This point to, sorry, let me come back. So this point to this point. So you can see, you saw the positive first. So this thing is minus VCE because voltage across these 2 points is collector E. So the voltage across these 2 points is VCE, voltage between collector and emitter, VCE. So minus VCE. And then you come down, and at this point you have 0 voltage. So this is also, so this will be your KVL in right. Okay. So this will be your KVL in left loop and this will be KVL in right loop. And you can solve these two equations and get whatever you want. And I will be giving you the questions in which we will be using these two loops. Okay. So now stability factor is something which defines that with temperature, how stable your transistor will remain. So the general formula for stability factor is this, which is given by beta plus 1. 1 minus beta DIB by DIC. Okay, so this kind of method, which is known as the base resistor method, this method is also known as fixed bias, fixed bias. And for fixed bias method, dIB by DC is 0. Why? Because you can clearly see from this equation that your base current does not depend upon IC. It depends upon VCC, which is constant. It depends upon VBE, which is constant. For silicon, it is always 0.7 volt, right? This voltage is always 0.7 volt for silicon. And your RB is also fixed. So your IB does not depend upon collector current. Even if your collector current changes, your IB is not going to change. So this thing is always 0. So if this thing is 0, then your stability factor is beta plus. So for such kind of methods, which is known as the fixed bias methods, so basically you have to fixed bias method or base resistor method. There are two names for this. For such methods, your stability factor is known as beta plus 1, where beta you already know is given for every transistor. So whenever someone gives you the transistor, they tells you that this is a value of beta. Now, stability factor is very large because beta is very large. Beta is usually 50 to 100, right? So beta value is going from 50 to 100. So stability factor is very large. So more is the stability factor, less is the stability. It's a reverse. If your stability factor is large, it means your stability of the transistor with the temperature is less. That is why in the fixed bias method, what happens is that this method is very easy to achieve. You can make this circuit very easy. But the problem is the stability of this circuit is very bad. Okay, so that you have to understand. So let's do one problem of the fixed bias method so that you understand that how the problems has to be solved. And the problem is very straightforward. And in this question, what is they are asking, they are giving you one circuit. Now, transistor circuit can be given to you in any form. So you don't have to worry about that because you simply have to apply Kirchhoff voltage. Okay, so you have to remember that are you applying Kirchhoff voltage law in open loop or closed loop? Okay, so if you are applying in closed loop, then simple rules which I explained yesterday. But if you are applying in open loop, then you have to start from one voltage, then use the same rule and equals to the final voltage. Okay, so that is the point. And then now let's see. So you have this question, and basically they are asking you what is the collector current and what is the value of VCE. So you know the value of IC and VCE is known as operating point. We covered in the last lecture that the value of IC, collector current, and VCE are nothing but known as the operating point. So basically they are asking you the operating point. And beta they are already giving you is 50. So let's start. So let's do first the Kirchhoff voltage law in left loop. So let's apply Kirchhoff voltage law in this. So let's begin from here. So first I'm applying in closed loop, right? So I'm applying my Kirchhoff voltage law in closed loop. So I can use my closed loop rules. So first I will begin and I will begin in this direction. So I am seeing negative side. So when I'm seeing negative side, I have to put plus. So now I'm putting plus 2. Then I move in this direction, go in this direction, go in this direction. I am going in the direction of current, and the current through this is IB because this current is entering the base, right? Base. So the voltage across this will be IB into RB. Since I'm going in the direction of current, so I have to put negative sign. And finally, now I'm going from base to emitter. So I should write VBE as well, right? So basically I should also write this minus VBE equals to 0. But in the question, it is given to us that neglect the small base emitter voltage. So they are saying that neglect this. Otherwise, if they do not say that neglect this, I have to say that minus VBE R minus VBE and then minus VBE. So because why minus? Because first I see positive, then I see negative. So minus VBE and then finally I will come back to the same position from where I started. So equals to 0. But now they are saying ignore this, so I'm ignoring this, and it is simply equals to 0. Okay. If they are not saying that ignore it, then always use VBE equals to 0.7. Okay, good. Now what I have to do, I have to bring RB on this side and 2 on this side. Now the value of RB is given to you as 100 kilo ohm, so I'm putting that value. So your IB comes out to be 0.02 milliampere. Okay. So always remember, whenever you're putting your resistors in kilo, your value of currents will be in milliampere. So you don't have to change the conversion units. So as long as you are putting your resistors in kilo, and most of the times your resistor will be in kilo. So whenever you are putting your resistors in kilo, you can simply assume that your current is in milliampere in that equation. Fine. So this is my current. So my IB current comes out to be 0.02 milliampere, or I can even write it as 20 microampere. Okay. So milli is 10 to the power minus 3 and micro is 10 to the power minus 6. So I can go from this to this by multiplying 10 power 3. So if I do that, I will get 20. Okay, good. Now Kirchhoff voltage law in right loop. So now let's do the Kirchhoff voltage law, but now I will apply in the right loop. So let's begin from here. So I'm going from here to here. So again, I see the negative first. So if I'm seeing the negative first, I have to use positive. So I will write plus 9. Then I go up. So now I'm moving in the same direction as current. You can clearly see here. So IC into RC, IC into RC. So, but I'm going in the direction of current, so I have to put negative sign here. So minus IC into RC. And then I reach here, and then there is positive here and negative here, and voltage between them is VCE. So now I'm jumping from positive to negative, so I will apply minus VCE equals to 0. Now on this hand, I can find IC as well, because I already know IB, and the formula I know is that if I know IB, then IC is nothing but beta IB. IC is nothing but beta IB. So IC equals to beta IB. I put the value of beta, I put the value of IB. So beta is 50, IB is 20 microampere. So final answer is 1. So my IC is 1. Now I can use this IC here. So it is 9. IC is 1 milliampere. RC, what is the value of RC? This thing. This is 2 kilo ohm. So 2 kilo ohm minus VCE. Fine. So milliampere, milli and kilo cancels each other. Milli is 10 ki power minus 3 and kilo is 10 ki power plus 3. So both of them cancels each other. So 9 minus 2 will give you 7. So the value of IC comes out to be 1 milliampere and value of VCE comes out to be 7 volt. So these are the two numbers. Okay. Now let's do one more problem on the similar kind of question. Now you can clearly see that you again have a fixed bias method or the base resistor method. Okay. So now your beta is 100. You have a silicon transistor. Silicon transistor means that your value of VBE is 0.7 volt. Means the potential here plus minus is nothing but 0.7 volt. Okay, fine. And then first thing they are asking you is draw the load line, DC load line. So let's draw the DC load line. In the last lecture, we studied that how to draw DC load line. On the x-axis, you have voltage, output voltage. So your output voltage is between C and E. So output voltage is between C and E. So output voltage is VCE. And your output current is IC. So IC. Now on the x-axis, you have to write VCC. What is the value of VCC? 6 volt. And on this axis, you have to write VCC by RC, right? So what is VCC? It's 6. And what is RC? RC is 2 kilo. So VCC by this, so this will be 3 milliampere. So you write 3 milliampere here, you write 6 volt here, and you basically connect the line from this to this. And you will get your final answer. Okay, so this is your load line. Okay. Now, second, determine the operating point. Operating point means nothing, but operating point means finding the value of VCE and finding the value of IC. Now, this is your homework. It is same to the last question. Only the values of resistors I have changed. So you can say use the same mathematics. How will you use the same mathematics? Now, let's start from here. Let me explain this question to you. So let's first do the right and then left. If I do the loop in right, so I will start from here. Now I am using the Kirchhoff open loop, right? You can see now you are applying the open loop. So you are not applying closed loop. So you're starting from 6. So if you're in open loop, if you're starting from 6, so write 6. So you're starting from 6, so I'm writing 6. Then I move in this direction. Okay. And then I see IB into this. So I can write IB into RB. And since I'm going in the direction of current, so negative side. Then I come here and I see positive, negative 0.7. So since I see positive side first, so minus 0.7. So IB can be written as 6 minus 0.7 is 5.3 and divided by RB, which is 530 kilo ohm. So if you are writing in kilo ohm, your answer will be milli. And if you solve this up, your total answer will come out with 10 micro. Okay, so simple mathematics, nothing else. Now, if you know IB, then IC you already know. How you know IC? IC is nothing but beta IB. If you multiply beta 100 and this is 10 microampere, your answer will come out to be 1 milli. So your IC comes out to be 1 milli. Then you can write the Kirchhoff voltage law in right loop. How you do that? So you begin from here, again open loop Kirchhoff voltage law. So you are going from here to here. So you are starting from 6. So start from 6. Okay. And then you come down, and then you see RC into IC. RC into IC, so that you are going in the direction of current, so you have to apply negative. So RC into IC, and you have to put negative. And then you go from here, positive to negative. So this is what? VCE. So you have to put minus VCE. So if you take VCE on other side, your 6 is 6. RC is what? RC is 2 kilo ohm. So RC is 2 kilo ohm. IC you have calculated as 1 milliampere, 1 milli. Kilo and milli cancel each other. So 6 minus 2 will be 4. So your operating point is 4 volt and 1 milliampere. This is your answer. Okay. They are also asking the stability factor. So stability factor is nothing but beta plus 1. So beta is already 100. So stability factor is 101. So this was the first method, which was base fixed bias method or base resistor method. Okay. Now the second method is known as emitter bias circuit. So this circuit looks something like this. Now you do not have any common voltage, but you have a common base, common ground. So this common ground is there, and this is common ground because all three are grounded. So you can either ground all of three individually, or you can just show one common ground. Now you can clearly see in the emitter side there is a one battery is there, which means emitter bias. Bias means applying battery. It means you have applied the battery on the emitter side. So now again, it's nothing new I'm going to do. The circuit is same. In most of the questions you don't even realize that which method it was or which circuit it was because the step is same. You basically have to apply the Kirchhoff voltage law. Now let's start applying Kirchhoff. So let's apply the Kirchhoff voltage law in this loop. Okay. So many people will think that this is an open loop. So you're going from here and coming here. So it's open. No, it's a closed. So you're starting from zero and this is also. This is 0 volt because it's grounded. It's 0 volt because it is grounded. So you're starting from ground and coming back to ground. So this is actually a closed loop. You're starting from ground and coming back to ground. So it's a closed loop. Okay. Because ground and ground can be connected to each other. Okay. So this is a kind of closed loop. So if it's a closed loop, let's start. So I'm applying a closed loop. So analysis. So I begin from here. I start from here. So I go like this. First thing I saw is IB into RB. I'm going in the direction opposite to that. So I will write minus IB into RB. Then here plus and this minus and this is VBE. So I will write minus VBE. Then I will come in the downward direction. So I am going like IE into RE. Again, minus IE into RE. And then there is this battery. So I will see my negative side of that. So I will write plus VEE. And then finally I am here. So this is equals to 0. So from here VEE comes out to be this thing. Okay. Now what I can do is I can do some more analysis and I can actually see that my IE and IC will almost be equal because emitter current is almost equals to the collector current and collector current can be written as beta into I. So let's put my value of IE here as beta into I. So this is VEE, then IB into RB, then VBE, and then this thing. This thing is beta into IB because IE is almost equals to collector current. Emitter current and collector current are almost equal and base current is very small. So I'm assuming that my emitter current is almost equal to collector current and collector current can be written as beta IB. So beta IB into RE. Always remember in transistor, the first current that we always find is base current. And once we know the base current, then we find the collector current by using the formula beta IB. Once we know the collector current, then we say that collector current and emitter current are almost same. This is the general steps which follows in almost all the problems. First, you find IB using the Kirchhoff voltage law loops, and then once you know IB, then you use the formula that IC equals to beta IB, and then in the final step you say IE and IB are almost same. Okay. So now I am putting IE as beta IB. So this is the equation I. Now in this equation you can put the values. You can put this value. You can put this value. You can put all the values, and if you put all of these values which will be given to you in the question, you can find IB. So once you know IB, then you can find IC, and IC and IE are almost the same. Now I can even apply Kirchhoff voltage law and write. So if I do that, I will start from here. So this is again closed because I'm starting from ground and again coming back to ground. So this is ground. So this is closed loop. So I start from here. So first thing is I say is negative side. So I will add plus VCC. So plus VCC. Then I'm going in the direction of, I'm going, and then I'm here. So that I'm going in the direction of current. So minus ICRC. So minus ICRC. Then I come here. So then I have plus here and minus here. So this thing is plus VCE. So I see plus first, so I write minus VCE. Then I come down, I come here, IERE, so I'm going in the direction of current, so minus IERE. And finally I see the negative of this, so I see plus, I will write plus. So plus VEE equals to 0. So this is my second equation. I already know IC, I already know IE. I can put all of these values and I can find VCE. Okay. So use these are the equations how you formulate it. Okay. So there is one previous year question which is given to you. Let's see that can we solve this question. Okay. So the question is given to us that this voltage is 20 volt. Okay. And collector voltage is also given to you. So this voltage is also. So VCE is given to you as 14 volt. And this is ground. But if it's little cut, this is little is image is little cut, but this is ground. Okay. So basically they are asking that how you will find R, and this is your homework. Okay. So basically now you have to do nothing else. You first have to write the open loop from here to here, and then you have to write open loop from here to here. So two open loops, and once you solve those two open loops, you will get your answer. I have solved this problem. You can look at this. Okay. Then this question also, again your homework. So how you do that? Again, the simple step. So first you can write the open loop from here to here. So you can start from here. You write a KVL from here, go here, till here, and back. So this is a closed loop. You're starting from ground and going from ground. So this is a closed loop. So you start from here. So you see minus first. So you write plus. Then you go in the direction. So you write minus IB into RB. And then this is minus 0.7 and this is equals to 0. Right? This is first loop. And then you can write the second loop. So second loop will be from here to. Okay. So two loops, and basically you have to solve these two loops and find the value of VCE. So they are asking you find the value of VC, and VC is same as VCE. Why? Because VCE can be written as voltage of collector minus voltage of emitter. And voltage of emitter is 0 because emitter is here and emitter is directly connected to the ground. Emitter directly connected to the ground means voltage of emitter is 0. So VCE is equals to VC. So you have to basically find VCE, and that thing will be same as VC. So they are basically asking you find VCE. So apply two Kirchhoff voltage law, one in this and one in this, and you will get the answer. Okay. So this was based on the two methods we studied in above. Okay. In both of those methods, the stability factor was very bad. Okay. So we have to improve on that. So next two methods which we are going to cover, in that the stability factor is little better. So these are the better stability factor methods in which we have the more stability. Fine. But these methods are difficult to achieve. On first two methods, they were very easy to obtain. You can easily find and use those transistors. But the problem in those transistors is that if your temperature is changing or some parameters are changing, the transistor will become very unstable. So there is something known as thermal runaway. If you do the more advanced electronics or electronics course, you will actually know that what is thermal runaway. Okay. Good. Now, third method is known as biasing with collector feedback. Collector feedback basically means that feedback word means that you take an output and then you bring it back to the input. So you can clearly see your output is collector and your input is base. And if you connect both of them together, it means you are connecting your output to input, which basically means you are giving the feedback. So your current goes from input to output, and then some of that current, not all of that current, some of that current is given back to. Then again, current goes from input to output, and some of that current is given back to them. So this is known as feedback. And one thing you have to remember is in physics or in electronics, whenever the feedback is given, the stability increases. It doesn't matter which device it is. As long as it is negative feedback, stability will be bad. And if it is positive feedback, feedback can improve and reduce stability depending on if it is negative feedback or positive feedback. But most of the time, the feedback is being used to improve the stability. So if you want to improve the stability, you have to give the feedback in a proper method. If you give it in the proper method, your stability of the circuit will improve. Okay, so the circuit is in front of us. This is the kind of circuit you have. And now you can clearly see that there is some current coming up, and that current includes two things. So that current is known as, first of all, I, and that current involves two things. One is collector current and one is base current. So this current I is flowing through this circuit. And then at this point, IB current goes here and IC current goes to the collector. So at this point, your current splits into two parts, IB and IC. But in this resistor, the current I is flowing and IE is made up of two things, IC into IB. Okay. So then collector current enters here and IB current goes here. Now what I can do is I can apply the Kirchhoff voltage law in left. So I start from VCC. So I start from VCC. Then I'm going in this direction. So the current through this is I. So it will be I into RC. I into RC. Since I'm going in the direction of current, so I have to put negative sign. Then I come here and then I go to the left loop. So I enter here. So I will write minus IB into RB, minus IB into RB. Then I will reach till here. Then it is positive, negative. This is VBE. So minus VBE. And then finally you are at the ground. So equals to. Okay. So this was an open loop. You can clearly see this is an open loop. So that is how I have done it. So now I can put, now this, I can bring all of the terms on the side. So your VCC comes out to be this. Now this I is nothing but IB plus IC. Okay. So the stability factor of this is lesser than beta plus 1. So stability factor of the last two methods was beta plus 1. But not for last two methods, but for first method it was beta plus 1. For this, the stability factor will be lesser than beta plus 1. So it is little bit more stable. Less the stability factor, more is the stability. Okay. So your S is less than beta plus 1, it means your stability has increased. Your stability factor has reduced, but stability is increased. Okay, good. Okay. Now there is a problem which is like this, and this is a very good question, that they're basically asking you determine the operating point. So how do you determine the operating point? So basically you have to tell the value of VCE and you have to tell the value of IC. Let's begin. So you start from here again. So 20. Then the I current is flowing through it. So I into resistance is 1. So I'm putting the values of in kilo ohm. So my current will be in milliohm. Then I come here and then I move in this direction. So minus IB into resistance 100. Then I come here and then VBE is 0.7. So 0.7 minus 0.7 equals to 0. So then I put my value of I. Then what is my I? I is made up of two things, IC plus IP. IC can be written as beta IB. So this entire thing will become beta plus 1 IB. Beta plus 1 is 101. So 101 IB. So I put my value of I as 101 IB. Okay. So I can put my value of I as 101 IB. So this will be 20 minus 101 IB minus 100 IB minus 0.7. So 20 minus 0.7 will be 19.3. And this will be 201 IB. So if I divide 201 IB will be equals to 19.3. So basically IB will be 19.3 divided by 201. And current will be in milliampere because the resistors were in kilo. So if you solve this, your value will be 0.096 milliampere. Now what will be your current? I you already know. I you know na 101 IB. So I is 101 IB. So IB value you have already found 0.096. If you multiply this, you will get answer 9.7 milliampere. So the value of current you have found out, which is 9.7 milliampere. Now you can easily see that your I is nothing but IC plus IB. So IB is very small. So your IC and I are almost same. Whatever is your IC, that is the same value for your I. Okay. So IC and I are very same. That is why you have actually found the I, but you have already also found the IC. Okay. So in operating point, you have to find two things, IC and VCE. So IC you have already found, which is 9.7 million. Okay. Now let's apply the Kirchhoff voltage law in right loop. So I will start from here. So 20. Then I will come down. So I am coming down. So minus I into 1. So minus I into 1. And then I will move from this point to this point, which will be minus VCE. So minus VCE and then equals to 0. So from there, VCE will be 20 minus I. I is 9.7 milliampere. So this thing comes out to be 10.3 volt. So VCE is 10.3 volt and IC is 9.7 milliampere. Now you have the similar question. This is a previous year question and this is also feedback method. So this is your homework. use this. It's an exactly same kind of problem. So try to do it and get an answer. And I have solved it. If any case, it is just a 3-step problem. You can easily do that. Okay. Okay. Now I want to come to the last method, which is known as the voltage divider. So we did 3 methods. One was base resistor. Then we said emitter biasing method. And in the last method, what we did, feedback method, collector feedback method. And now it is voltage divider. So voltage divider method is the most used. Okay. Maximum number of times the problem in the laboratories or in the applications, the transistor is biased in voltage divider method. Why? Because it is most stable. And in this, what is happening actually is I want to explain you the rules here. The happening is that you have a voltage VCC. And that voltage VCC is divided into 2 parts, into 2 resistors. One is R1 and one is R2. And I want to explain to you that R1 and R2 both are in series. Why? Because let's say the current is flowing in this direction as I. Let's say the I current is flowing here. And then some of that current will go here. And that current is known as base current. And base current is negligibly small. So whatever current was coming here, the same current will be flowing here because almost no current goes here. So let's say if the 1000 current was coming from here, then 1 will go here and 999 will go here. So this and this has almost the same current. So that I can say that if the current in this resistor is I, then the current in this resistor is also I. When the current in 2 resistors is same, we say that those two resistors can be assumed to be in series. So now you have 2 resistors. One is R1 and one is R2. What is the voltage difference between these 2 resistors? Voltage at this point is VCC and voltage at this point is 0 because this is ground. So the voltage difference between them is VCC, right? So the voltage difference between R1 and R2 is VCC. So now your voltage will divide into 2 parts. In this, some voltage will be dropped here and some voltage will be dropped here. So V1 will be the voltage here and V2 will be the voltage here. And I am interested in finding V1 and V2. First of all, let's find that what will be the total current in the circuit. So total current in the circuit will be total voltage. So total voltage is VCC divided by total resistance. So total resistance, since they both are in series, and in series the resistors add up. You remember it from the class 12, you studied that in the series the resistors add up. So if I add up the resistors, so R1 and R2 will add up. So I will get R1 plus. So current will be equals to VCC by R1 plus. Perfectly fine. So you have found the total current in this. Current is same in both. So you have basically found out this I1. This I1 you have found out. And this is equals to V by R1 plus VCC by R1 plus R2. Now this current R1 and R2 in current in both will be same. So what will be the voltage across R1? Voltage across R1 will be I into R1. So let's put the value of I, which is VCC R1 plus R2 divided by into R1. So this is your voltage 1 and voltage 2 will be I into R2. So basically VCC into R2 by R1 plus R2. So this is your voltage across V1 and this is your voltage across V2. If you do some mathematics, you will actually realize that your stability factor is 1, which is a very good stability. Okay, so your stability factor is 1, which is very, very small stability factor, which means your stability is very high for this circuit. So whenever you have a voltage divider, voltage divider biasing, you will actually see that your stability factor is 1, which is very stable. Okay. Now let's solve the previous year question so that of this problem, so that you actually understand that how to solve the problems. So in this circuit given below, so whatever is in the black marks, I have written that. So that was not given to you in the question. But basically in the question, they were asking you that find the value of VCE, means voltage between this point and this point. This is asked and they are saying that neglect VBE. So no voltage is applied between this point and this point. And beta is given to you as 100. First of all, this is a voltage division. So first of all, divide the voltages. So you have a total 10 volt. Some voltage will be across this and some voltage will be across this. Let's find V1. So V1 formula we just studied, it is VCC into R1 divided by R1 plus R2. So total voltage 10. Then this resistance because we are finding voltage across this. So this resistance R1 divided by total resistance R1 plus R2. So VCC is what? 10 volt. And uh, and similarly, what will be V2? V2 is VCC into R2 divided by R1 plus. Let's find VCC. VCC is 10. What is R2? R2 is 5. R1 plus R2 is 10. So your voltage is 5. So the voltage across this point, this is 5 volt. This point is 0 because this is grounding. So this is 0. So this point will be 5. Only then the voltage across this will be 5 volt, right? So voltage across this will be 5 volt because this is 0. This thing is 0. And we have just found that voltage across this resistor is 5 volt. So if this is 0, then this point is 5. Okay. So we have calculated that. So voltage across this point is 5 volt. If I do V1, that will also come out to be 5. So voltage across V1 is also 5. And you can clearly see that this point is 10 because this is connected to 10 and this point is 5. So 10 minus 5 is 5. So the voltage across this is also 5 and this is also 5 because 5 minus 0 is 5 and 10 minus 5 is also 5. So the voltage across both the resistors, voltage difference across both the resistors is 5. Now we will use the Kirchhoff voltage law. So we will start from here because we already know the voltage at this point is 5 and we will start from here and then we will end here. So this is an open Kirchhoff voltage law. So I am starting from 5. So I will write 5. Then there is no voltage across VBE. So I am ignoring that. And then I go here. So IE into RE. IE into RE will be IE into RE. And RE value is 10 kilo ohm. So I put my this as 10. So my IE will come out to be 5 by 10, which is 0.5 milliampere. So whatever is your emitter current, that will approximately be your collector current. So I have find both IE and IC. Okay. Now I can use the Kirchhoff voltage law in this loop. Okay. And if I do that, I will start from 10. I'm starting from 10 and then minus IC into RC. So 10 into minus IC into RC. RC is 5 kilo ohm. You can clearly see here. 5 kilo ohm, 5 RC. And then I see plus and minus. So VCE. So minus VCE. So minus VCE. And then I come down and I come here. So this will be IE into RE. RE is 10. So minus 10 into IE. So minus 10 into IE. So I put the value of, so VCE I bring it here. So this 10 is 10. IC value is 0.5 milliampere. 5 into 0.5. IE value is also 0.5. So 10 into 0.5. So this becomes 10 minus 2.5 minus 5. This thing is 2.5. So your VCE comes out to be 2.5. So that is how you solve the problem of voltage division. So one thing is very clear from the lecture itself, that there are going to be 4 methods. If you can identify that which method is there or which kind of circuit is it, it will help you a lot. And second, there is a very fixed method in which the question is going to come. So if you solve all the VK method solved examples, there is nothing which is going to come outside that. And third, you have to be very good in applying Kirchhoff voltage. And there is always going to be 2 loops in which you will apply Kirchhoff voltage law. One will be left loop and one will be right. In left loop, if you go, you will see VBE. In the right loop, if you go, you will see VCE. So that is going to be. And third thing, which is very important, is all the questions are coming from common emitter configuration. So that is the maximum number of times you will see that. Okay. So that's all for today lecture. I will see. And a transistor is over here. So now we can move to the next part. Okay. So that's all for today. I will see you in the next class.